In this video, we'll look at different methods by which you can expand a file system to multiple disks. First, let's look at the concept of logical volume managers. A logical volume manager is a method to allocate space on storage devices, and it's more flexible than conventional partitioning schemes. LVMs support the addition of multiple disks and can also split up a single disk into multiple volumes. Now, some of the techniques that LVMs allow users to use is concatenation, whereby multiple disks are added together into a single volume and they will be used as the disks fill up. Then there's data striping, where data is divided into multiple blocks and spread out over multiple disks, and it also allows for live resizing and migration. LVMs are implemented in the device driver stack of the operating system. Now let's look at some of these techniques. First, we'll talk about file striping. File striping is nothing but splitting a file into blocks to be distributed among multiple disks. In this example, we have a file which contains about 9 blocks, and as you can see, they're divided and individually distributed among 3 disks. But the division is also non-sequential in the sense that the first block is on the first disk and the second block is on the second disk, and so on. File striping can be done at multiple levels. The most common type of file striping is block level striping these days, where a block of a particular defined size, say a few kilobytes to even multiple megabytes, is defined to be the striping unit. Similarly, we have byte and bit level striping. Now we'll look at mirroring. In mirroring, we keep copies of data on separate disks. So in this example, we have a file with 9 blocks, but we are using 3 disks to store that same file, and they all contain copies of the same file. Now, mirroring provides error recovery. So if a disk is lost, then you can always get some of the data that was lost on the disk from another disk because there is a mirror copy of that data. However, as you can imagine, mirroring is expensive. It requires additional disks, and you do not gain capacity as you add disks to a mirror set. So even if you have 2 1 terabyte drives, if you use them in a mirroring arrangement, you only get a single terabyte of usable space. Another problem with mirroring is that write performance could be slow because you now have to write data to 2 different spots, and it depends on how advanced the disk controller is. But at the same time, read performance can be enhanced because if there are multiple processes that are trying to read a single file, you could read them from 2 disks in parallel. Now let's look at some error detection and correction methods that are typically used with disks. There is the notion of simple parity. So a parity bit that counts the number of bits that are equal to 1, and there are variations of this, which is even or odd parity. It can detect errors, but it may not be able to correct errors without additional data. Hamming codes is a parity scheme that contains multiple parity bits that can detect and correct a limited number of bit fluctuations. And finally, we have Reed-Solomon encoding, the details of which are a little too advanced to cover in this video, but it's a block-based parity scheme. So here we have an example of a file that is striped across disks, and we introduce the notion of an additional parity disk. So we have parity for every 3 blocks, and all of the parities are stored on a dedicated parity disk. Now that we've discussed some of these individual schemes, we can now talk about RAID. RAID is short for Redundant Array of Independent Disks. It's a method by which you can combine multiple disks to improve capacity, performance, and/or reliability, and the way in which you combine the disk will dictate how each of these parameters are affected. Now, RAID can use multiple techniques such as mirroring, striping, and parity, and we'll look at each of the individual RAID schemes. And different RAID levels denote different configurations. So let's look at the first RAID level, which is RAID 0. This is simple data striping. It improves performance, but as you can imagine, if a single disk is failed, then you lose all of the data that is across the set. So in our example on screen right now, if you lose either 0 or 1, then you lose all of the data because the other data may not make sense without having all of the blocks that were striped across the 2 disks. Next, we have RAID 1, which is data mirroring. In this, the total capacity is divided by the number of disks in the set. But at the same time, you can tolerate a disk failure in RAID 1. So in this example, if disk 0 or disk 1 fails, it doesn't matter because you can retrieve the data from the other disk. So RAID 0 is great for performance and RAID 1 is fantastic for reliability. Now that we look at a couple of additional RAID levels, and some of these RAID levels are ones that are not in use today but are included for historical reasons. RAID 2 is a bit level striping scheme with Hamming code parity on dedicated disks. So this is the example that we discussed in the parity disk scheme. So we have a file that is striped, and the striping level now is at the bit level. And then you have Hamming code that is generated and stored on a special disk, an additional disk known as a parity disk. In RAID 3, the level of striping is increased from bit to byte, and you still have dedicated parity disks. And finally, in RAID 4, you go to block level striping with dedicated parity disks. Now, these are included for historical reasons because they have the concept of a dedicated parity disk. And as more and more research came through about RAID, it is found that you don't necessarily need to have a dedicated parity disk. Instead, you can have the parity distributed among multiple disks, and those sort of define the next couple of RAID levels. In RAID 5, you have block level striping with parity distributed across the disks. So now in this example, you don't need to have a dedicated parity disk. Instead, you distribute or you stripe the parity across multiple disks. RAID 6 is basically the same as RAID 5, but you have basically the notion of double parity. So you can now tolerate 2 disk failures in a set. So we looked at some of the basic RAID levels from 0 to 6. Now there are ways in which you could actually combine multiple RAID levels, and we'll look at 2 such examples. There's the idea of RAID 0 plus 1, which is mirrored stripes. Now if you're given a file, you can construct a stripe set or RAID 0 set, and what you do is you can mirror them in RAID 1 configuration. So you kind of get the benefits of both RAID 0 as well as the reliability of RAID 1. However, as you may notice, you're using a lot more disks. You could also do the opposite, which is RAID 1 plus 0, and this is the idea of a stripe of mirrors, which is pretty much the opposite. So you have a RAID 1 mirror set, and then you stripe them across in RAID 0 fashion at the higher level.